So I wanted to say something about bipartite graphs. These are an important class of graphs that I'll define in a second. A bipartite graph is one where the vertices of the graph, V, can be divided into two collections, V1 and V2. So you can put some of the vertices in V1 and some of the other vertices, the rest of the vertices, in V2. And all of the edges in the graph, if there are any edges, will always go from a vertex in V1 to a vertex in V2. So you'll never see any edges among vertices in V1, and you'll never see any edges among vertices in V2. So here's an example of a bipartite graph. There are no vertices among these, no edges among these three vertices, and there are no edges among these three vertices. So all the vertices can be divided into two groups, the ones on the left and the ones on the right. Here's another bipartite graph. You have these two vertices. Notice there are no edges between them. There's no edge between them, and these two vertices. So there are two collections of vertices, and there are no edges between those among the vertices in each collection, so it's also bipartite. Another bipartite graph could be like this. Okay, so anytime you have this division into two groups of vertices, it's easy to see that all bipartite graphs can be validly colored using two colors. Why is it easy to see? Well, for any bipartite graph, you can divide its vertices into two groups, group 1 and group 2. So you can color all the vertices in group 1, say red, and all the vertices in group 2, say blue. Since there are no edges among vertices in group 1 or in group 2, it's a valid coloring. Any edge that does appear will have a vertex from on one side that's been colored red, and a vertex from the other side that's been colored blue. So any bipartite graph can be colored validly using two colors. In fact, it's easy to see that being a bipartite graph is equivalent to being a two validly colorable graph. So that is to say, if a graph is bipartite, then the graph is two colorable. This means it can be validly colored with two colors. And if a graph is two colorable validly with two colors, then the graph G is bipartite. So we've said that if it's bipartite, then it can be colored using two colors. So that proves this implication. Why is this implication true? Well, if a graph is two colorable, why does it mean it's bipartite? Well, let's say it's two colorable. That means you can color it with red and blue. This is just a proof sketch. It's a simple proof. So we can two color the graph using red and blue. So let all the vertices that are colored red, this will correspond to your first set of vertices, and let all of your vertices colored blue, that'll correspond to your second set of vertices. Since it's validly colored, that means that there are no edges among the red vertices, so there are no edges among vertices in V1. And again, since it's validly colored, that means there are no edges among the blue vertices. So there are no edges among the vertices in V2. So the edges can only connect vertices from V1 to V2 and vice versa. So this proves that being bipartite is equivalent to being two validly colorable. Let me prove something else relating two colorability to cycles. So here's a claim that we'll prove. So if a graph is two colorable, so if it can be colored validly using two colors, this implies that all cycles in the graph, if there are any, are of even length. So let's think about this claim. It's saying if we have a graph, we know it's two colorable. This implies that any cycles that appear in this graph have to be of even length. So how do we prove this? Well, it's by contradiction. So let's assume that the graph is two colorable, and so let's assume, by way of contradiction, that there is an odd length cycle. Okay, so that means somewhere in the graph, 1, 2, 3, 4. Okay, somewhere in the graph, there has to be a cycle of odd length. Now, I've drawn one here that's of length 5. Maybe it's of length 7 or 9. It's not going to matter. All that's going to matter is that it's of odd length. So this vertex here, it's validly two-colored. So let's assume that it was colored, so case 1. Okay, so let's look at this vertex V. Let's assume that V is colored blue. Okay, so if V is colored blue, it means this vertex has to be red, this vertex has to be blue, this has to be red, this has to be blue, and that's a contradiction because V was originally blue. Again, if V was blue, it means this must be red, blue, but now we have two vertices that are attached to each other, both colored blue. That's a contradiction. What about if V is red? If V is red, well, then this is red, this would be blue, red, blue, red. So again, we'd have two vertices colored red, colored by an edge. You can see that this had nothing to do with the length of the cycle being 5. It had everything to do with the length of the cycle being odd. And it didn't matter what the initial coloring of V was. So what did we do? So I guess this was case 2. So basically we said, okay, let's assume the graph is two colorable, and there's an odd length cycle. But we came to a contradiction. This two coloring is no longer valid if there's an odd length cycle. You can't have odd length cycles because you need these colors to sort of alternate with the right parity. So so this proves that if a graph is two colorable, all cycles are of even length. And we're going to prove in the next video something more interesting. We're going to prove the converse, namely that if all cycles in the graph are of even length, then it is two colorable.